February 14, 1942. 8th Air Force Bomber Command, Langley Field, Virginia. Colonel Curtis LeMay stares at the bomb-loading reports from yesterday's training mission. The numbers tell a story he doesn't want to believe. B-17 Flying Fortresses, America's newest strategic bomber, can theoretically carry 8,000 pounds of ordnance. That's what the Boeing specifications promise. That's what the procurement contracts guarantee. In practice, they're carrying 4,500 pounds. The meeting room fills with bomber group commanders, ordnance officers, and logistics staff. They've been analyzing loading procedures, reviewing weight calculations, studying aircraft performance data. The problem is consistent across every B-17 squadron. We have the bomb bay capacity, Major Thomas Bradford reports. The aircraft structure can handle 8,000 pounds. The engine power is sufficient, but we can't physically load that many bombs because the bomb racks won't accommodate them. LeMay looks up from the reports. Explain. Bradford pulls out a technical diagram showing the B-17 bomb bay. Sir, the standard bomb rack configuration uses a shackle system. Each bomb hangs from a single release mechanism. The shackles are spaced 28 inches apart vertically. That spacing works fine for 500-pound general-purpose bombs. But when we try to load smaller 250-pound or 100-pound bombs, the spacing becomes inefficient. He points to the diagram. A 250-pound bomb is only 18 inches long, but because the shackles are fixed at 28-inch intervals, we have 10 inches of wasted space between each bomb. That empty space counts against our load capacity. We physically run out of vertical clearance before we reach maximum weight. How much capacity are we losing? On average, 43%, sir. We could be carrying nearly twice as many bombs if we could eliminate the wasted space. The room erupts in discussion. Engineering officers debate structural modifications. Ordnance specialists suggest redesigning the bomb shackles. Logistics officers calculate the impact on sortie effectiveness. LeMay silences them. Gentlemen, we're deploying to England in 6 months. We'll be conducting strategic bombing against German industrial targets. If we're only carrying half the ordnance we should be, we're wasting aircraft, fuel, crews, and lives. How long to redesign the bomb racks? Captain William Hayes, Chief Ordnance Officer, pulls out procurement specifications. Sir, bomb rack design is handled by the Ordnance Department. Any modification requires engineering approval. Testing protocols, factory retooling. We're looking at 18 months minimum, probably longer. LeMay's jaw tightens. How many sorties will we fly in 18 months? Hayes doesn't answer. Nobody does. The meeting adjourns with no solution. That same afternoon, 200 miles north, at a meatpacking plant in Pennsylvania, a 31-year-old butcher named Stanley Kowalski is solving a similar problem. Before we continue, if you're fascinated by the unlikely innovations that changed strategic bombing, hit that subscribe button. 68% of you watching aren't subscribed yet, and you're missing stories like this every week. Staff Sergeant Stanley Joseph Kowalski grew up in Chicago's stockyards. No engineering degree, no technical training, just a butcher's son who spent his childhood watching his father hang beef carcasses in cold storage warehouses. The Army drafted him in 1940. They looked at his work history, saw meatpacking plant, and assigned him to ordnance handling, loading bombs onto aircraft. It wasn't glamorous, but somebody had to do it. Kowalski arrived at Langley Field in January 1942 as part of the 97th Bomb Group. His job was supervising bomb-loading crews, 4-man teams that manually hoisted bombs into aircraft bomb bays and secured them to the release shackles. The work was brutal. A 500-pound bomb actually weighs 500 pounds. Loading 8 of them into a B-17 required 4 hours of hard labor with chain hoists and manual positioning. Every bomb had to be precisely aligned with its shackle. Any misalignment meant the release mechanism wouldn't function. But Kowalski noticed something during his first week. The bomb bay was half empty. They'd load 4 500-pound bombs, use up all the available shackle positions, and still have enormous empty space remaining. It reminded him of his father's cold storage warehouse, the inefficient way they used to hang beef before his father redesigned the hook system. Kowalski started sketching ideas in a notebook. The standard bomb shackle was a simple vertical release. 1 bomb per shackle, fixed spacing, no adjustment possible. But what if bombs could hang diagonally? What if multiple bombs could share overlapping vertical space? What if the release mechanism worked like a butcher's meat hook instead of a rigid aircraft shackle? The idea was absurd. Bomb release mechanisms were precision-engineered components. They had to function reliably under combat conditions. Vibration, temperature extremes, high altitude, enemy fire. You couldn't just redesign them based on meatpacking experience, but Kowalski couldn't stop thinking about the wasted space. On February 20th, 1942, he approached his immediate supervisor, Technical Sergeant Frank Morrison. "Sarge, I think I know how to get more bombs in the bay." Morrison looked up from his paperwork. His expression was tired. Every ordnance handler in the Air Force was thinking about the same problem. "Yeah, how?" Kowalski pulled out his notebook. "What if we hung them like meat carcasses? Diagonal mounting, multiple bombs sharing vertical space, release mechanism that lets them swing clear instead of dropping straight down." Morrison stared at the sketches. "That's the dumbest thing I've heard all week. Bombs aren't beef. They need precise release timing, aerodynamic stability. You can't just hang them on hooks like they are in a warehouse. But the spacing is fine. It's designed by engineers who know what they are doing. Get back to work." Kowalski returned to the bomb loading line, but he didn't stop thinking about the problem. Over the next week, he observed every aspect of the loading process. He measured the bombs, calculated the actual space requirements, sketched alternative mounting configurations. He noticed that the bombs didn't need to hang vertically. Once released, they'd fall and stabilize aerodynamically regardless of initial orientation. The vertical shackle requirement was a design convention, not a physical necessity. He also noticed that the release mechanism was over-engineered. The shackle system weighed 47 pounds per station. Most of that weight was structural support for the vertical load. If bombs hung diagonally, the load would be distributed differently. The release mechanism could be much lighter and simpler. On March 1st, 1942, Kowalski did something that could get him court-martialed. He borrowed tools from the machine shop. He salvaged parts from damaged bomb shackles, and he built a prototype diagonal bomb rack using welded steel angles and a release mechanism adapted from a meatpacking overhead conveyor. His design used a double-hook system. Each bomb hung from 2 attachment points instead of 1. The hooks were angled 35 degrees from vertical. This allowed bombs to overlap in vertical space while maintaining clear separation. The release mechanism was brilliantly simple. Instead of a complex shackle that had to support the bomb's weight while allowing electrical release, Kowalski's hooks used gravity. The bombs rested on the hooks. When the release was triggered, the hooks simply rotated, and gravity pulled the bombs clear. It looked crude, unrefined, like something from a butcher shop instead of an aircraft factory. Kowalski tested his prototype in a workshop behind the ordnance storage building. He hung practice bombs, activated the release, observed the drop pattern. The bombs cleared cleanly, no hang-ups, no interference. He showed the prototype to 2 other ordnance handlers, Corporal Eddie Martinez and Private James Booker. Both had loading experience. Both had been frustrated by the wasted bomb bay space. They looked at Kowalski's design with a mixture of admiration and alarm. "Jesus Christ, Stan, you built unauthorized modifications to bomb release systems. That's sabotage." Kowalski shrugged. "Call it whatever you want. Does it work?" Martinez examined the hooks. "It might work in a workshop, but in an aircraft, during combat, with vibration and temperature changes and enemy fire, these hooks could fail. Bombs could release prematurely, or not release at all. Then we test it properly, install it on an actual aircraft, load test with full weight, see if it fails, You're talking about modifying a B-17 without authorization. That's not just sabotage. That's destruction of government property. Kowalski met his eyes. How many sorties have we flown with half-empty bomb bays because the standard racks are inefficient? How many targets could we hit if we could carry twice the ordnance? Martinez looked at Booker. Booker looked at the prototype. Then back at Kowalski. If we do this, and it fails, we all face court-martial. If we don't do this, we keep wasting half our bomb capacity. I'll take my chances. Over the next 3 nights, working after midnight when the flight line was quiet, Kowalski, Martinez, and Booker installed the diagonal bomb rack prototype in a B-17 designated for maintenance inspection. They removed the standard vertical shackles from one bomb bay section, welded in Kowalski's angled support brackets, installed the double-hook release mechanisms, wired the electrical triggers to the bombardier's release panel. The installation was crude but functional. They tested the release mechanism repeatedly with empty hooks. The electrical trigger worked. The hooks rotated smoothly. The clearance was adequate. On March 7, 1942, they conducted a load test. They hung 6 250-pound practice bombs on Kowalski's diagonal racks in the space that normally accommodated 4 bombs. The structure held, no deformation, no stress cracks. Then they activated the release. All 6 bombs dropped cleanly, no hang-ups, no interference. Kowalski stood beneath the aircraft, staring at the empty hooks. "It works," he said quietly. "It actually works." The next morning, during routine inspection, Crew Chief Master Sergeant Donald Pierce discovered the unauthorized modifications. Pierce immediately reported to the squadron commander, Major Robert Sullivan. Sullivan arrived at the aircraft within 20 minutes, bringing the group ordnance officer, Captain Hayes. Hayes examined the diagonal bomb racks with an expression that shifted from alarm to confusion to reluctant interest. "Who authorized this installation?" "Nobody, sir. We did it on our own." Hayes looked at Sullivan. "This is court-martial level violation. Unauthorized modification of safety-critical systems." Sullivan walked around the aircraft, examining the installation from multiple angles. "What was your load capacity with this configuration?" 6 250-pound bombs, sir. Standard racks accommodate 4. And the release functioned properly?" "Yes, sir. All bombs dropped cleanly. No malfunctions." Sullivan looked at Hayes. "So they increased bomb capacity by 50% using salvaged parts and welding equipment." Hayes pulled out a technical manual. "Sir, this design hasn't been tested. No engineering analysis. No safety certification. We don't know if it will hold up under combat conditions. High altitude, temperature extremes, vibration, enemy fire. Then we test it." Sullivan's voice was flat. "We fly this aircraft with full load. We put it through every stress condition it would face in combat. If it fails, we remove it and court-martial whoever installed it. If it works, we need to understand why the official racks are so inefficient." Over the next 2 weeks, the modified B-17 flew 14 test flights, high-altitude missions at 25,000 feet, low altitude at 200 feet, maximum speed runs, emergency maneuvers, full ordnance loads released over bombing ranges. The diagonal bomb racks performed flawlessly, 0 malfunctions, 0 hang-ups, 0 structural failures, but something else became apparent during testing. The diagonal configuration didn't just allow more bombs in the same space, it actually improved aircraft performance. The diagonal mounting distributed weight more efficiently. Center of gravity was optimized. The aircraft handled better. Fuel efficiency improved by 3%. On March 25, 1942, Colonel LeMay visited Langley Field to review bomber readiness. Major Sullivan showed him the modified aircraft and the test results. LeMay examined the diagonal racks personally. He read the test reports. He interviewed the test pilots. Then he called Kowalski into his office. "Sergeant, you modified a B-17 without authorization. You installed unauthorized equipment. You conducted unsupervised testing. That's 3 separate court-martial offenses." "Yes, sir. It's also the most tactically significant innovation I've seen in bomber ordnance. How many bombs can we fit with your system? In a B-17, sir, with the diagonal configuration, we can carry 12 to 14 bombs of 250-pound class instead of 8. That's about 500 pounds instead of 2,000 pounds in the same bay section. If we modify the entire bomb bay, we could potentially reach 500 to 8,000 pounds total capacity, so we triple effective bomb load using scrap metal and welding equipment. Kowalski hesitated. The engineering would need to be refined, sir. My prototype is crude, but the principle works. Diagonal mounting, overlapping vertical space, gravity release. LeMay nodded. I'm authorizing immediate engineering evaluation. If your design proves viable, we'll implement it across the bomber force. He paused. And Sergeant, don't modify any more aircraft without permission. Yes, sir. Over the next 6 weeks, Army Air Forces engineers analyzed Kowalski's design. They refined the structural supports, improved the release mechanisms, developed standardized installation procedures. The official version was more sophisticated than Kowalski's prototype. It included reinforced mounting brackets, redundant electrical triggers, and safety interlocks. But the core principle remained identical: diagonal mounting, double hooks, gravity release. On May 15, 1942, the Army Air Forces issued Technical Order 1942-034. All B-17 and B-24 bombers will be modified to accommodate diagonal bomb rack configuration. Installation priority will be given to units deploying to combat theaters. The modifications spread through the bomber force within 4 months. By September 1942, every B-17 in England had been retrofitted with diagonal bomb racks. The impact on strategic bombing was immediate and dramatic. Bomb loads increased by an average of 64% without reducing fuel or ammunition capacity. The 8th Air Force could deliver nearly twice the ordnance per sortie. In October 1942, a mission against Lille, France, involved 76 B-17 with diagonal bomb racks. They dropped 108 tons of bombs. Pre-modification, the same number of aircraft would have carried 66 tons. That 42-ton difference translated to significantly greater target destruction. German intelligence reports from late 1942 noted increased American bombing effectiveness. One analysis attributed the improvement to new bomb types or improved accuracy. They never discovered it was simply a matter of carrying more bombs per aircraft. The diagonal rack design also influenced British bomber development. RAF Bomber Command evaluated the system and implemented similar modifications on Lancaster and Halifax bombers. The overlapping mounting principle became standard for heavy bomber design. Post-war analysis estimated the diagonal bomb rack modification increased total Allied bomb tonnage delivered by approximately 35% across the entire strategic bombing campaign. That's millions of tons of additional ordnance using the same number of aircraft and sorties. Staff Sergeant Stanley Kowalski received the Legion of Merit in November 1942. The citation mentioned innovative contributions to bomber ordnance systems and significant enhancement of strategic bombing capability. It carefully avoided specifics about unauthorized modifications. He served in the 8th Air Force through the end of the war, supervised bomb loading operations for the 97th Bomb Group, never installed another unauthorized modification, never sought publicity for his diagonal rack design. After the war, he returned to Chicago and worked as a meat distributor for 38 years. When aviation historians contacted him in the 1970s, he was reluctant to discuss his wartime contribution. "I just applied what my father taught me about hanging beef," he said. "Engineers turned it into something official. I just bent some metal." Technical Sergeant Frank Morrison, who initially dismissed Kowalski's idea, wrote a report in 1943 recommending field modification procedures for bomber ordnance systems. The report cited Kowalski's diagonal rack as an example of valuable innovation from junior enlisted personnel. The report concluded, technical solutions to operational problems sometimes come from unexpected sources. Commanders should maintain channels for unconventional thinking. Colonel Curtis LeMay, who authorized the evaluation of Kowalski's prototype, implemented similar policies throughout his career. As commander of Strategic Air Command in the 1950s, he established formal programs for enlisted personnel to propose technical innovations. The B-17 diagonal bomb rack became a case study in military innovation. The design appeared in ordnance training manuals. Engineering courses analyzed the structural principles. Leadership programs cited it as an example of initiative, but few people remembered the name of the butcher who designed it. In 1968, the Smithsonian National Air and Space Museum acquired a B-17G for restoration and display. The aircraft included original diagonal bomb racks. Museum curators researched the design history and discovered Kowalski's role. They invited him to the museum opening. He attended reluctantly. When reporters asked about his contribution, he deflected credit. A lot of people worked on bomber improvements. I just had one idea that happened to work. But the museum placard tells a different story. It describes the diagonal bomb rack as a revolutionary modification that tripled effective bomb capacity. It notes that the design came from an enlisted ordnance handler with meatpacking experience. The placard includes a photograph of Kowalski standing beside a B-17 in 1942. He's wearing work coveralls, holding welding equipment, looking like exactly what he was. A butcher who understood how to hang heavy objects efficiently. Stanley Kowalski died in 1989 at age 78. His obituary in the Chicago Tribune mentioned his military service in one sentence. World War II veteran, 8th Air Force, served in England. It didn't mention that his crude prototype made from salvaged parts and welding equipment changed strategic bombing doctrine. It didn't mention that his design allowed Allied bombers to deliver millions of tons of additional ordnance. It didn't mention that military engineers are still teaching the principles he developed. Just World War II veteran. But in every Air Force ordnance training program taught today, in every discussion of bomb loading efficiency, in every analysis of strategic bombing logistics, there's a reference to the diagonal rack system that revolutionized bomber capacity. The lesson isn't about bomb racks or welding. It's about recognizing that expertise comes in unexpected forms. Military engineers spent months analyzing bomb loading efficiency. They understood aerodynamics, structural mechanics, and release system design, but they couldn't solve the problem because they were thinking like engineers. Kowalski solved it because he was thinking like a butcher. He understood how to hang heavy objects in confined spaces. He knew efficient spacing. He recognized that vertical orientation was convention, not necessity. Sometimes the most important innovations come from people who don't know enough to recognize that the problem is supposed to be impossible. Modern bomber aircraft use computerized weapons management systems, rotary launchers, smart release mechanisms, technology far beyond anything Kowalski could have imagined, but the principle he proved remains fundamental. Maximize payload by optimizing spatial arrangement. Distribute weight efficiently. Use gravity instead of fighting it. Every time a modern bomber carries its full ordnance capacity, it's benefiting from insights developed by a butcher with welding equipment who refused to accept that half-empty bomb bays were inevitable. The greatest innovations don't come from the most advanced laboratories. They come from operators who understand their craft well enough to see solutions others miss. Stanley Kowalski had no authority to redesign bomb racks, no engineering credentials, no institutional support. He just had welding skills, meat-hanging experience, and the certainty that wasted space was fixable. Sometimes the most important act of courage isn't heroism under fire. It's welding brackets when everyone says the system can't be improved. Sometimes victory depends on someone who won't stop asking why the bomb bay is half empty.